Hello, welcome to another module in this massive open online course. So, we are looking at compressive sensing, alright, where you try to compress not after the sensing process, alright. So, you try to compress during the sensing process itself by making much fewer number of measurements in comparison to the dimension of the signal, and then later try to reconstruct the signal from the very few measurements made, alright. So, let us continue our discussion on compressive sensing. Let us see what are the necessary conditions for this. So, we are looking at compressive sensing, and what we have seen is one thing that has to be done, we are doing is essentially you have a measurement vector y of equals phi times x bar, and this is your sensing matrix. And you have m measurements y1, these are your m measurements, you have your matrix phi, and I am going to draw this vector much larger than y bar purposefully, because we are making much fewer measurements than the length of the signal x. Okay. So, this is your measurement vector, and this is your signal, and this is your sensing matrix, and remember this is an m cross n matrix, and what we have is that m is less than or equal to n, that is we make significantly fewer measurements, or let us say m is significantly lower than L, alright. Now, if you view this as a system of equations, then we have m as a number of equations n equals number of unknowns. So, our number of equations is less, significantly lower than the number of unknowns. So, simple linear algebra tells us, high school level linear algebra tells us that one cannot reconstruct the vector x bar of length n, which basically comprises of n unknowns, from simply m equations, since the number of equations is much lower than the number of unknowns. So, this is an underdetermined system, alright, so as to say. So, one cannot uniquely determine x bar. Therefore, this system, this sensing system has to satisfy certain special properties in order to recover x bar from the observation. Now, what are those conditions, or what are the properties the system has to satisfy? That is what we want to look at. So, in order to recover or reconstruct x bar from y bar, the sensing system must satisfy some conditions. What are those conditions? For instance, let us look at the first condition. The first condition states that it must satisfy some condition. The first condition states that measurements are not simply in the time or space. These are not simply in time or space, okay. These are not simply in time or space, rather they have to employ noise like measurements have to employ noise like or one can say pseudo noise or noise like these have to employ pseudo noise or noise like waveform, or let us just say noise like waveforms. Measurements have to employ what is the meaning of that? The meaning of that is, if you look at this sensing matrix phi, okay, if you look at, remember we said we have the sensing matrix which is m cross n, which means there is m rows and m columns. If you look at each row, which we are denoting by phi 1 bar transpose, phi 2 bar transpose, phi m bar transpose. So, these are the rows. So, each row of the sensing matrix, each phi I bar transpose, which is the ith row, has to be a random noise this has to be a noise like waveform, which means that it has to be something very random. It has to look like a random or a pseudo random sequence. For instance, like some random sequence of either can be a random sequence of -1, 1, or it has to be some random noise like waveform such as Gaussian, so on. So, it has to be either a random noise like or a random sequence, ones, -1, so on. So, each row, that is if you denote the ith row by phi I bar transpose of the sensing matrix phi, this has to look like noise, this has to look purely like noise. It cannot be one followed, it cannot, so the matrix phi cannot look like an identity matrix, 1 followed by 0, 0, 1, zeros, it cannot look like an identity matrix. Each row has to look like, and these rows have to look like independent realization of the noise waveforms, alright. And thereby when you are making the measurement, what you are doing is you are taking the projections of the signal on this noise like waveform. So, when you are making the measurements, you have your y1, y2, ym, which is equal to phi 1 bar transpose, phi 2 bar transpose, phi m bar transpose times x bar. So, this is equal to phi 1 bar transpose x bar, phi 2 bar transpose x bar, phi m bar transpose x bar. So, each is a projection. So, each measurement, if you look at this, each measurement I, which is phi I bar transpose x bar, the measurement yi is phi I bar transpose x bar, this is the projection of x bar. This is the projection of x bar on the random noise like waveform phi I bar. this is the projection of x bar. So, what you are doing when you are taking these measurements, such as each row of phi, the sensing matrix is a noise like waveform, and when you are taking the measurement, what you are doing is nothing but taking the projection of this x bar, a linear combination of x bar, using this noise like waveform, which is the rho phi I bar. So, the ith measurement is phi I bar transpose x bar, alright. So, that is an important property of the sensing matrix. Okay. Now, let us talk about the vector x bar. Now, the vector x bar itself has to satisfy an important property, and this I would say is the important property of most important property of x bar. The vector x bar, and I am going to introduce this terminology which we are going to use very frequently, x bar has to be sparse, and this is a very important property. X bar has to be sparse. What is the meaning of this? Remember, when we say something is sparse, when we say an area is sparsely populated, which it means that there are very few people in that, alright. This is sparse, implies that it's very few, it's sparse in some object implies there is very few numbers of that sparse object. In particular, if it is sparsely populated, a country is sparsely populated implies that there are very few people in there. Now, x bar is sparse implies that, very simply, it implies that a large number of entries of x bar are 0, only very few entries are non-zero. So, this implies that, basically what this implies is that large number of entries. So, sparse implies large number of are 0, only very few entries which I am marking by these x's, for instance, only very few entries are non-zero. Only very few entries are non-zero. So, a large number of entries of x bar are 0, very few entries. So, x bar is a sparse vector or, so x bar is sparse, or alternatively, and this is typically what happens, or x bar equals psi, some matrix psi times alpha bar. So, x bar is n cross 1, this alpha bar is n cross 1, and psi is an n cross n basis, such that alpha bar is a sparse vector, that is alpha bar equals sparse, implies alpha bar has very few So, either x bar is sparse, the vectors that you are trying to recover, or more importantly, and this is what happens more frequently, like an image, x bar can be expressed as a linear transformation of a sparse vector. For instance, if you take an image, if you look at it in the spatial domain, it is not sparse, but if you take, for instance, the wavelet transform, it is an excellent example. If you look at the wavelet coefficients of an image, then they are sparse, very few coefficients are non-zero. So, therefore, I can have an image x bar which is psi times alpha bar. So, let us say this is image, these are the wavelet coefficient and this is your wavelet transform matrix, linear transform okay. So, x bar is sparse or x bar can be expressed in terms of alpha bar which is sparse, and therefore, now if you substitute this, the sensing model becomes y bar equals phi x bar equals phi psi times x bar equals phi tilde times x bar, okay. I am sorry, phi psi times alpha bar, and if you denote phi psi as by phi tilde, the effective sensing matrix, this phi tilde now becomes your effective sensing matrix, and now alpha bar is sparse, and you still have the same relation. This is m cross 1, this is m cross n, and this is n cross 1. Now, in this model it is as if you are trying to sense the vector alpha bar which is in the wavelet domain, okay. Now, once you get the wavelet coefficients, naturally you can reconstruct the image, right, because image and wavelet, they have a one to one correspondence. If you have an image, you can represent in terms of its wavelet transform, right. If you have the wavelet transform, the wavelet coefficients, you can reconstruct the image, alright. But the wavelet coefficients satisfy a very important property, which is that this coefficient, the wavelet vector of wavelet coefficients, is sparse, and that is very amenable to compressive sense, and this is what frequently happens, and the model can be extended, right. So, your y is equal to phi times x bar, you substitute for x bar psi times alpha bar, so it becomes phi psi into alpha bar, and now you reconstruct alpha bar from alpha bar which is sparse vector, sparse signal recovery or compressive sensing, and then you get the image from the wavelet coefficients, alright, or x bar from alpha bar using x bar equal to psi alpha bar. So, once you get alpha bar, use x hat equals psi alpha hat to obtain estimate x hat from alpha hat, okay. So, that is what you do, okay. And now, if you look at this phi tilde matrix, this has to contain noise like waveforms, okay. So, phi tilde, which is your effective sensing matrix, has to comprise of this has to comprise of noise like waveforms, okay, or contains noise like waveforms, okay. Now, how to reconstruct this alpha bar or x bar? If x bar is sparse, how to reconstruct? Let us assume that x bar is sparse and phi contains noise like waveforms. Now, the question that we want to ask is how to reconstruct x bar? To reconstruct x bar, what we have to do is we have to enforce the sparsity. Remember, x bar is a sparse vector. So, we have to enforce sparsity. So, how to reconstruct x bar? The answer is enforce sparsity. What does it mean to say enforce sparsity? Implies we have to somehow impose a condition that x bar contains a large number of, remember we said x bar is a sparse vector. So, we have to enforce this sparsity, which implies that we have to ensure that the reconstructed vector x bar is such that a large number of elements are zeros, only some elements are non-zero. So, which implies we have to ensure that large number of elements of x bar are 0. We have to ensure that large number of elements of x bar are 0. Okay. This is what in fact ensure that large number of elements of x bar, okay, large number of elements of x bar are 0, alright. So, that x bar is sparse, and this is precisely what is enforced by what we call the L0 norm. That is, if you denote the L0 norm of a vector, this is L0 norm, like similar to L1, L infinity and L2 norm. This is the L0 norm, okay, this is L0 norm, and L0 norm, this equals the number of non-zero elements of x bar, okay. So, this is precisely what you want to minimize, the number of non-zero elements of x bar, which is L0 norm, okay. For instance, let us say you have the vector x bar equals 0 0 2 0 minus 1 0 0 0, okay. Now, L0 now look at this, is 8 elements, but only 2 non-zero elements. Which implies, if you look at L0 norm of x bar, that is simply 2, alright. So, very simple, all you have to do is count the number of non-zero elements of x bar, alright. Whatever is the number of non-zero elements, that is the L0, nothing else to be done. So, it is very simple, the concept of L0 norm itself is very simple. So, this L0 norm concept is very simple, but there is a problem. So, in fact, the non-zero elements we are not concerned with the values of the non-zero elements, we just have the number of non-zero elements. We are not concerned with, observe here, unlike the other norms, not at all concerned with values of something that is strange. For instance, this could have been 2 comma 1, and in fact, if you have another x tilde which is 0 0 3 0 5 0 0 0, non-zero elements are 3 comma 5, and if you look at L0 norm of x tilde, that is also 2, alright. The interesting part is we are not at all concerned with what are the values of these non-zero elements, we are only concerned with the number of non-zero elements. That is the most interesting thing about the L0 norm, and that is what in fact makes it very complex, this problem. And therefore, so the optimization problem for now, reconstruction, and therefore, and this is very interesting, therefore optimization problem for reconstruction of x bar is the same thing that we talked about. We have the sensing model, we want to minimize the L0 norm, okay, and now subject to the constraint that y bar equals phi times x bar. What is y? Y bar is observation vector, that is what something that we have already seen. Y bar, phi is sensing metric, x bar is a vector that we are trying to estimate, x bar. So, when you minimize, so this is basically this is what we mean by enforcing sparsity. This is enforcing sparsity because we are minimizing the L0 norm, that is minimizing the number of non-zero elements. So, this is the relevant optimization problem. And why do we need this? We need this because m number of equations m is less than or equal to n, which implies that number of equations is less than or equal to number of unknowns, okay, and therefore one has to exploit sparsity. So, reconstruction is only possible exploiting, because as we said, if you treat this reconstruction only possible via reconstruction only possible via exploiting sparsity. So, what does this mean? You are enforcing sparsity, which means you are trying to find here, finding the sparsest vector. Find the sparsest vector which satisfies the observation model, okay. So, that is what this optimization problem is. That satisfies the observation model y bar equal to 5 x bar. So, if you are trying to find the sparsest vector, okay. Now, what is, so now we have written an optimization problem, like similar to several optimization problems that we have seen before. We have an optimization problem, okay. You might think that you can solve it similar to fashion that we have done before. You have an optimization objective plus Lagrange multiplier. The problem with this is, this optimization problem not only is the objective non-differentiable, this optimization problem is highly non-convex. If you look at the L0 norm x bar 0, L0 norm, this is highly convex. This is highly non-convex, implies very difficult to solve above optimization problem. Very difficult to solve over. Consider a simple technique. What you can do is, for instance, let us say you have m elements, or n equals size of x bar. What you can do is set only one non-zero element of x bar, solve it, alright. You will have one equation, you will have one unknown, you will have only one unknown, but the non-zero unknown can be in any of the n positions. So, you will have to solve n systems, okay. And then similarly you can have two non-zero elements. The two non-zero elements can be in any of the two locations. So, you have NC2 such combinations. So, you have to solve NC2 systems. So on and so forth. If you look at this, total number of equation systems that have to be solved is n choose 1 plus n choose 2 plus so on, and this will be 2 to the power of n, or 2 to the approximately, you do not need to get into the exact number. What you can see is this rises exponentially, okay. So, this is of the order 2 to the power, or you can write order 2 to the power of n. So, total number of systems which is highly complex. For instance, if you have a signal vector x bar of dimension 100, then you have to solve 2 to the power of something of the order of 2 to the power of 100, which is impossible, alright. That cannot be solved by any known computer either now or in the very far future, right. So, the point is that this problem, although it is very simple to state the optimization problem, it is an extremely complicated optimization problem to solve. Now, if you look at, for instance, the L0 norm, what is the L0 norm? If you look at, for instance, L0 norm equal to L0 norm, if you look at a two dimensional plane, this one point has L0 norm equal to 0 because that is the origin. Now, this axis other than origin, if you look at this axis, that has L0 norm, because on the axis you have only one non-zero element. So, this is rest all of the plane other than axis and origin is. So, if you look at L0 norm less than or equal to 1, that comprises only of the axis. So, axis so if you look at this object, it is highly non-convex. So, if you look at the L0 norm ball, the L0 norm ball, this is the this is literally the L0 norm ball. Which is basically highly non-convex, and that is the problem in solving this optimization problem. Alright. So, you would like to make very few measurements, agreed. Projections on noise like waveforms, agreed. The vector x bar is sparse or it is sparse in some appropriate domain, x bar equals psi times alpha bar, but the problem is that the problem, eventually the problem that has to be solved to enforce sparsity, which is basically minimizing the L0 norm, that has an exponential complexity. It is an NP hard problem, and which is therefore practically impossible to solve for large signals x bar, that is signals of the size, let us say even 20 samples or 25, it becomes very difficult, exceedingly difficult, and if with 100 samples it is impossible to solve, and therefore one has to come up with other ingenious techniques to solve this optimization problem, and that is basically at the heart of compressor sensing. What are the other techniques that can be used to solve this optimization problem, which we are going to look at in subsequent modules, that forms the basis for compressor sensing, and that is what, in fact, these techniques have revolutionized the field of compressor sensing. Alright. So, let us stop here and continue in the subsequent modules. Thank you very much.